Right before us we are having a diagram. This is a diagram, this is a sphere, and this sphere is in a jar, or call it a very long cylinder that is having some thick fluid. Now when we drop this ball down so that it starts flowing into this liquid, it's definitely going to, if it is water, if this was water, this ball will just fall through with ease. If this was probably glue, a jar full of glue, and then you drop this ball in, now of course it's going to take some long time before it reaches the bottom. Now this glue, for example, if this was glue, this ball would have difficulty going through that glue up to the bottom because this glue is thick. The thickness of that glue is as a result of what we call viscosity. We discussed this in our previous sessions. That viscosity is simply the resistance to motion within fluids. Now, this is a body that is flowing through this viscous fluid. And any body that is flowing through a viscous fluid will experience a kind of retarding force or a resistive force because of the viscosity of the fluid. Now, that viscous force, that retarding force, is what we are calling the viscous drag. This viscous force that is experienced as a result of the viscosity of the fluid is what we are calling the viscous drag. And this viscous drag, in other words, we can say, is the force that opposes motion of objects that are dropping through the fluid. So right here we have another diagram that illustrates it better. We have a solid sphere here, and probably it's having a force. It's moving in that direction with a certain force F. But we are having a viscous fluid with all these layers in the opposite direction. So it means that as this force is propelling this solid sphere through this fluid, this solid sphere experiences what we call a viscous drag. Now this viscous drag depends on some factors. Now some of the factors that affect this viscous drag, we have, of course, what causes that drag, the resistance to motion. We have a coefficient of viscosity. It's a factor in the magnitude of the viscous drag. We also have the size of the body, or if this body, of course, if the body is small, the amount of resistance that will be experienced by a small body will not be the same as the amount of resistance that will be experienced by a big body. So meaning, if we're talking about a solid sphere, in this case we'll be talking about the radius of the sphere. The radius of the sphere will influence how much resistance it will face as a body. Then also we have what we call the velocity of the body through the viscous fluid. Of course, if the body is thrust with a very high force or with a very low force as it's going through that viscous fluid, the velocity with which that body is being thrown or it is going through the viscous fluid will affect the viscous drag. And this is what we want to experiment in today's video. We need to look at those parameters. Now, those three parameters that I've talked about that affect the viscous drag, which are the coefficient of viscosity, the size of the body that is flowing through the viscous fluid, and the velocity of the body, is what is the basis for what we call Stokes' law. Combine those factors, we will say that force is directly, the viscous force or the viscous drag is directly proportional to the coefficient of viscosity. It has something to do, as in, it also has something to do with the radius, this radius or the size of the body of the solid sphere, and then also the viscous drag or the force also has something to do with the velocity with which this thing is falling. Now, we do not know. We need to investigate whether these things are directly proportional or inversely proportional by investigating the indices X, Y, and Z. And that is what we are going to do right now. So let's find the indices of X, Y, and Z. After knowing those indices, we will be able to identify the relationship perfectly, whether these things are exactly directly proportional or inversely proportional. We're going to use dimensions to find these indices. So definitely, of course, using dimensions, we need to find the dimensions of force. That is going to be equal to the dimensions of this constant K, multiply that by the dimensions of the viscosity, coefficient of viscosity to the power x, and the dimensions of the radius to the power y, and the dimensions of velocity, that is to the power z. Now definitely this is going to be the dimensions of force is mass times acceleration is lt to the power -2 is going to be equal to k. Now this constant is dimensionless. Constants do not have dimensions, so that is ignored. That is multiply that by the coefficient of viscosity. We found the coefficient of viscosity earlier as m L to the power -1, T to the power -1, and all this is to the power x. Multiply that by r. R is the length, so that is L. R is the radius to the power y. Multiply that by v to the power z. Now v is velocity. Velocity is L t to the power -1, and that is to the power z. Now I have not gone into the specifics of how we come to Lt to the power -1, how we come to ml -1 to -1, and how we come to all this. Now regarding the coefficient of viscosity, I explained how we come to this in our previous sessions. You just need to go to the videos in the playlist. But then regarding this and that and how we come to this, I have another video on how we find dimensions. I'll put the link in the description below for you. So we continue. We have to, after coming up with this, we need now to equate the corresponding indices. The corresponding indices in this case, we're going to start with m, mass. So when we look at m, we equate the indices for this side and for that side. So for this side we have m, the index here is 1. So we shall say for m 1 on this side of the equation. Then this side of the equation we have m here is to the power 1. 1 times x is x. So 1 is going to be equal to x this side. And so you realize that x already is equal to 1. That is for m. Then let's get to L. So coming to L, you realize that L here is this side. L is to the power 1. So we have 1 is going to be equal to L, this side of the equation. L we have -1x. So it's -x. Then we have L to the power y. 1 times y is plus y. Then we have L here is to the power 1 times z, so plus z. Now of course in our first expression we already got our value of x as 1. So if we substitute for 1 here, this is going to become 1 being equal to -1 plus y plus z. And then you find that when this comes this way, it becomes 2 is going to be equal to y plus z. This is probably our second expression. This was our first expression. So that is what we come up when we do with L as y plus z is equal to 2. That's how L turns out. So let's compare the indices for T. If you look at T, we have T this side is -2. So we have -2 is going to be equal to T this way. We have -1 times x, which is -x. Then we have another T here, -1 times z is minus z. And then we shall end, but in our first expression here we have x as 1. So we substitute for 1 here, it becomes -2. It's going to give us -1 minus z. And this is going to become, when this -1 comes this way, it becomes -2 plus 1 becomes -1 is equal to -z. It means that our value of z here is 1. So from here we have sorted that z is 1, x is also 1. So since we have x, we have z, we can go ahead and find y. So from this expression, if we substitute for z here and call this z1 right here, if we are to call substitute for 1 here, you realize that here 2 is going to give us y plus z. which z we got as 1 here. And so you realize that our value of y here is going to be 2 minus 1, which is 1. So from our working here, as we use dimensions, we realize that the value of x is 1, the value of z is also 1, and the value of y is equal to 1. So that expression becomes the viscous drag F, therefore, is going to be equal to the dimensionless constant times the coefficient of viscosity to the power x, which is 1, times r, whose index is 1, times v, and still to the power 1. And according to experimental observations, it was found that the value of k, this constant, is equal to 6 pi. So what does that mean? It means that this now becomes that F, the viscous force F, is going to be given by 6 pi times the coefficient of viscosity times R times V. And this becomes Stokes' law. So this expression defines Stokes' law. In this video, we get to discuss the vertical motion of a body when it is falling through a viscous fluid. Right there, we have a diagram that is describing a solid sphere. This solid sphere is falling through what we call a viscous fluid. This viscous fluid could be porridge, it could be glue, it could be engine oil. Those fluids that are thick, those are the viscous fluids, the ones that are hard to penetrate because of their viscosity and thickness. So now this body, when it is falling through the viscous fluid, there are some forces that are acting on this sphere. These forces are the upthrust force that is derived from Archimedes' principle. We also have this force capital F called the viscous drag, the one that we discussed in our previous session, where we had the basis for Stokes' law. And then also we have the force that is making this fall down in the liquid. And that force is what we are calling the weight of this sphere. The weight that is propelling this sphere to fall through this viscous fluid. So we have these three forces. We have this force down and these two forces up. Now, we assume that this sphere is falling through this, let's assume this thing is very tall and it's falling through a very tall jar that is full of engine oil, for example. So at the beginning, this weight is bigger, or it is bigger than these two forces combined. In other words, the downward forces are bigger than the upward forces. And because the downward force is bigger than the upward force, therefore, there is an acceleration as this sphere is dropping down the fluid. But after some time, it's going to happen in such a way that as this thing goes down, the downward forces are going to be equal to the upward forces. That happens because as this sphere continues to go down, the viscous drag keeps increasing. Remember, according to Stokes' law, that as the velocity of this thing keeps increasing, because the velocity keeps increasing. So as the velocity keeps increasing, the viscous drag also keeps increasing, because the viscous drag F and the velocity, those two are directly proportional according to Stoke. We covered that in the previous session. So as that continues, this ball continues to fall through this viscous drag, the downward forces eventually equalize with the upward forces. And now when the downward forces equate or are now equal to the upward forces, you realize that now this body or this sphere stops accelerating, and so it starts moving at a certain constant velocity. Now when it starts moving at a constant velocity, because now there is no more acceleration, the resultant force on this thing is now zero, since the upward forces are now equal to the downward forces. That velocity it will have attained is what we call the terminal velocity. So if I may define what terminal velocity is, we can say that terminal velocity is the maximum constant velocity that is attained by a body when it is falling through a viscous fluid. Let's look at this in terms of a graph. What I'm trying to say is this. that at the beginning the weight of this ball is bigger than the upward forces. The downward forces are bigger than the upward forces, and as a result there will be some level of acceleration as a result of the resultant force. But it's going to reach a point whereby the resultant force on this body is zero, and so it means that this body will start moving through this viscous fluid at a constant velocity. Now when it starts moving at a constant velocity, that constant velocity it's moving at is what we are calling terminal velocity, and by definition, terminal velocity is the maximum constant velocity that is attained by a body when it is falling through a viscous fluid. So let's take a look at this. We have this solid sphere right here. It is falling through this viscous drag, this fluid, the viscous fluid, and we are saying that when terminal velocity is achieved, the weight, which is this acting downwards, the downward forces are equal to the upward forces, which happens to be the upthrust and the viscous drag. When these two are the same, it means that this body is falling through this liquid at terminal velocity. And now we want to use this to find the expression for terminal velocity. So what we are going to do, one, we are going to first find the expression for weight, the weight of this ball. So it means, of course, we know that weight is going to be equal to mass times gravity. So we need to find the mass of this ball and the acceleration due to gravity. Then we also need to find the upthrust that is experienced by this ball. The upthrust experienced by this ball, we get that from Archimedes' principle, which states that a body that is wholly or partially immersed in a fluid is going to experience an upthrust which is equivalent to the weight of the fluid that is displaced. So it means for us to get the upthrust here, we simply need to find the weight of the fluid that has been displaced. And of course, finding the weight of the fluid that has been displaced requires that we know the volume of this sphere and the density of this sphere. Then we also have what we call the viscous drag. Of course, now the viscous drag, capital F, we get that by quoting Stokes' formula. Stokes' formula has got velocity in it, and the velocity in it there is going to be the terminal velocity. So now let's get to it. We need to find the expressions for this. We want to come up with an expression for terminal velocity of this body that is falling through this viscous fluid. So let's get started with the viscous drag, F. Now for us to be able to get the viscous drag at terminal velocity is given by 6 pi times the coefficient of viscosity times the radius times the velocity. Now the velocity in this case, we have denoted it as V subscript T, and V subscript T stands for the terminal velocity because the ball is falling at terminal velocity. So that is the viscous drag. This is the expression. And now, of course, the other thing that we need to know is that the density of the sphere is denoted by rho. The density of the fluid, we shall denote it by that. Then the terminal velocity is V subscript T, which we are using here in this expression. Then the coefficient of viscosity is denoted by that. Then the radius of the sphere, we shall be using R. These are the symbols we shall be using in this. So for viscous drag, F is given by 6 pi times coefficient of viscosity times the radius of the ball times the terminal velocity. So we have this expression for this. Now let's go on to the expression for the upthrust. Again, from Archimedes' principle, we know that upthrust is equivalent to the weight of the fluid that has been displaced. And the weight of that fluid that has been displaced is given by mass times gravity. Now, of course, gravity is a constant remain, but now we do not know the mass of the fluid. So mass of the fluid can still be given by density times volume. That is coming from this. Now, the density of the fluid, we already got that as, from our earlier expressions, we said that density of the fluid is given by that. So density of the fluid is that. Multiply that by the volume of the fluid, which is V. Multiply that by gravity. Now the volume of the fluid that has been displaced is equivalent to the volume of the sphere because it is the sphere that is displacing. So the sphere can only displace its own volume. So the volume of the liquid that has been displaced, or the volume of the fluid that has been displaced, This V is equivalent to the volume of the sphere, multiply that by gravity, which is G. So the volume of the sphere is what is here as 4 over 3 pi r cubed. This is the volume of a perfect sphere, multiply that by gravity, then the density of the fluid, and then we come up with that expression. And that expression we've come up with is simply the expression for the upthrust, right there. So this is the expression we come up with for upthrust. So now that we've got the expression for upthrust, let's go ahead and find the expression for the weight of the sphere that is falling through. So how is that given? The weight of the sphere is given by mass times gravity, of course. So gravity remains. Then for mass can be given by density times volume. Now the density, we have that. Now according to our write-up, we say that density of the sphere is given by that. So this is the density of the sphere. So that's density of the sphere. Multiply that by the volume of the sphere, which is given by 4 over 3 pi r cubed. This is the formula for volume of a sphere. Multiply that by gravity, and so the weight, which so happens to be mass times gravity, ends up being this. So this is the expression for weight. So we have gotten our weight. So we have the expression for this, we have the expression for upthrust, we have the expression for the viscous drag. So we are going to go ahead and these expressions we've got, we're going to go ahead and substitute them in this expression so that we're able to get an expression for terminal velocity. And this is exactly what we've done here. The weight of the of the ball, this is the weight of the ball. We got it from here. Weight is that, substituting there. Then it's going to give us the upthrust experienced by the sphere or the ball as it falls through the viscous drag, which is this. And that was got from here. Then we have the viscous drag, which viscous drag we obtained from this expression right here, like we had explained earlier. So now we go ahead and find the expression for terminal velocity Vt. So making this the subject of the formula, of course this whole expression will come that way, and this remains this way alone. Let me start with this. So it's going to become 6 pi times coefficient of viscosity times r times the terminal velocity is going to be given by this minus that. So it's going to become 4 over 3 pi r cubed times coefficient of viscosity times gravity minus this, which is 4 over 3 pi r cubed density of fluid times gravity. So now you realize that this and that, this is the same. So we factorize out some stuff. So this becomes 4 over 3. That is going to become pi r cubed times gravity. So gravity into, this is the density of the sphere minus density of the fluid. That is going to be given by 6 pi. So going ahead to make Vt the subject of the formula in this case is going to become terminal velocity is going to give us 4 pi r3g into density of the sphere minus density of the fluid. Divide, this is 4 over 3. Divide that by 6 pi times coefficient of viscosity times r. Now this pi and that pi will cancel out, and of course you remain with your terminal velocity, the expression. When you divide 4 over 3, divide that by 6, this is going to give us 2 over 9. This is r. Of course there is an r here, it disappears. This is r cubed, so it disappears. This 3 remains 2, so this becomes r squared times g. Like that into, so this is our expression for terminal velocity. Now that is, we can use this to find terminal velocity of a sphere that is falling through a viscous fluid, or you can, if you want to find the coefficient of viscosity of the fluid where a sphere is falling through, you simply, these two can flip sides. So it means that this expression can also still be written as, this comes here, this is that is going to be given by 2r squared g, divide that by 9 times terminal velocity into the density of the sphere minus the density of the fluid. we are going to describe an experiment that can be used to determine the coefficient of viscosity using Stokes' law. So of course this is going to be apparatus. We are going to use a very tall jar like that with a very viscous fluid. By that I mean a very thick fluid, and with definitely we are going to get a solid sphere that we are going to use to drop at the top. When you drop that solid sphere at the top, it is supposed to fall through. But now on this very tall jar, we are going to mark off two places. We are going to mark off just any two places along the tall jar where we anticipate that this solid sphere will be dropping through at a terminal velocity. So we mark it M1 and M2, and we take note of that height through between those markings. So the first thing we are going to do is, first of all, we need to know the density of this viscous fluid that we are using. So if we are using engine oil or we are using porridge, we need to know the density that we are using. And after knowing the density of what we are using, of course, like I had earlier said, we are going to mark 2 points along the jar, and we get the height, which in between we have called that height H1, and then thereafter we get a solid sphere. Now again, still this solid sphere, we need to know its density and its radius. And after when we know those, we are going to get that solid sphere whose density and radius we know, and then we are going to gently drop it centrally in that viscous fluid. Of course, when you gently drop it there, it is going to drop down into that very tall jar. And as it is dropping down, you take note on when it hits or it passes the mark M1 up to when it reaches mark M2 as it's dropping through that very tall jar. And so when as it's falling through, you probably have a stop clock. So as it is falling through, when it goes just past M1, you start your stop clock. Then as it's moving, it comes and goes past M2, you stop your stop clock, and then you take note of the time that has been taken for this ball or this solid sphere to fall from M1 to M2. And when that happens, you go ahead and find the terminal velocity. Now we know this is finding terminal velocity experimental. You know that velocity is given by distance over time, right? Or you know that speed is given by distance over time. So it's the same. Speed and velocity. Velocity is just a scalar quantity, but these two are more like the same units. So velocity is the same as density, distance over time. Let me call this distance S over time. So it's the same thing here. We are looking at a ball that is falling through this fluid with no acceleration at constant speed, and so that constant speed can be given by the distance divided that by time. So the distance in this case is the H1, and the time is the time you got on the stop clock. So it means that you go ahead and find the velocity, and that is the terminal velocity Vt. So we find it like that, of that ball that has fallen through, and we use that expression to find the terminal velocity. So we shall denote it as V0, or you can call it Vt like we've been doing before. Is going to be given by h, which so happens to be the distance and the time taken for that ball to fall through point M1 to M2. So after doing that, you can go ahead and find the coefficient of viscosity of this fluid. How? So now that we have our terminal velocity viscous subscript t given as h over t, then we can go ahead and calculate the coefficient of viscosity using this expression. This is the coefficient of viscosity of the liquid, the viscous liquid that we are dealing with, and we got this expression we derived this expression in our previous session. So that is how we can go ahead and find the coefficient of viscosity. After calculating the coefficient of viscosity using this expression that we derived in our previous session, we repeat this experiment. How do we repeat it? It means that we have different solid spheres of different radii. Maybe this is radius R1. You get a radius that is of radius R1, you drop it through, you find the terminal velocity by getting your stop clock. As this solid is falling through, you observe when it has just passed M1, you start your stop clock, then it moves, it reaches M2, you stop your stop clock, then you go ahead and find the velocity that was experienced by that ball of radius R1 by quoting this formula that the speed is going to be equal to distance divided by time, the distance in this case being the height, h1, divide that by the time. So you repeat this expression, this same experiment, using another ball of another radius, let's call it R2. Then you do the same. Then you get another ball with a different radius, R3. You do the same procedure, you get another ball of R4, you do the same procedures. In other words, the terminal velocities V subscript T are measured for different solid spheres with different radiuses. So after doing this, then you go ahead and tabulate your results. Of course, as you tabulate your results, you're going to tabulate results with you're going to have a column for the terminal velocity you've been getting. Then you're going to have another column for the radius, the terminal velocity that is corresponding to the different balls of the different radiuses you've been getting. Now in your table of results, you need to include R squared. So you're going to get these R squared and include them in your table right there. And after doing that, you tabulate your values, including values of R squared. Then you go ahead and start doing the math. Now from our previous session, still we derived this expression. We derived the expression that that the terminal velocity can still be given by this expression. And from this expression, you realize that when we were carrying out our experiment, we were getting terminal velocities, and in our table of results we have R squared. Now you realize that Vt and R squared, this is in the form of y is equal to mx plus c, and for those of us who do maths, y is equal to mx plus c is a straight line is a linear form of an equation. This 2 is a constant times this g. G is gravity is constant, 9 is a constant, coefficient of viscosity of the liquid. We are using the same liquid, so this figure does not change. We have the density of the sphere, we are using the sphere of the same density, the same kind of sphere, so it doesn't change. Then the density of the fluid also doesn't change, we are using the same fluid. From all this, you realize that this expression that is in black is constant, and what is changing according to our experiment, the things that we are varying are the terminal velocity we are getting as a result of using solid spheres of different radii. Since these two are the ones that are changing, realize that all this thing is in the form of y is equal to mx plus c, where y is the same as our terminal velocity, and our value of x is our R squared. And this value of m, which so happens to be the gradient, represents this whole expression in the middle. So in other words, if we went ahead and drew a graph of y against x, and we drew a graph, and the graph was such that the gradient of this graph is m. M is the slope. Now, this value of y would stand for Vt, the terminal velocity, and this value of x would stand for R squared. And so if we are to draw a graph, the slope of that graph would be this expression in between, and that is exactly what we do. We draw a graph of Vt, which is in meters per second squared, against R squared, which is in meters squared, and get the slope of that graph, which we shall call slope m. And this slope of the graph is equal to the expressions that are constant in our expression. Our value of m here, this is equivalent to 2g times this expression, which is that, divide that by 9 times the coefficient of viscosity. So that is the slope. Our value of m is equal to this. And now that we have our value of m, and the objective of our experiment here is to find the coefficient of viscosity using Stokes' law. So we make the subject of the formula in our next step, and you realize that we can get the coefficient of viscosity by this expression, with m being the slope of the graph that we attained from our experiment. And this is how we can experimentally determine the coefficient of viscosity of a fluid or a viscous fluid using Stokes' law. This brings us to the end of this video. Thanks for watching. Feel free to check out other excellent videos on the channel and don't forget to subscribe. For Kisembo Academy, this is Arnold Rangakuramia helping you manifest excellence.